So usually when we're talking about electrical circuits, so we talk about a resistor, we're talking about an element in an electrical circuit. If you've ever taken something apart and looked at the circuit board, you see these little things that are usually sort of little ceramic cylinders, and they're soldered to the circuit board. And for various reasons, when building an electrical circuit, we want components or parts of that circuit to have a certain resistance, and we do that by constructing these little circuit elements. Like I said, they're usually made out of some sort of ceramic. That has a much higher resistance than you could ever achieve with a piece of wire of a reasonable length. Like I said, I'll give us some homework problems to calculate how much copper wire it would take to have the same resistance as one of these little several kilo ohms or even mega ohm resistors. Notice that all these photographs of resistors, they have these little colored stripes on them. This is something that's been around for decades and decades to show the resistance of a resistor just by looking at it. Resistors have something on them typically called the resistor color code, where the different stripes on the resistor tell you something about the resistance. And there's a 2-digit code and then a multiplier telling you whether it's tens or hundreds or thousands or millions of ohms, and then a tolerance telling you to what percentage you can guarantee that that resistor's resistance is known. I actually can't read the resistor colored code because I am slightly colorblind, and so when I look at the resistor color code, I really don't see a whole lot of difference between the brown, the red, and the orange stripes, which make it very difficult for me to decipher the code. This isn't something that is really important unless you're going to go into electrical engineering and need to be able to pick up a resistor and tell by looking at it what its resistance is. You can always just connect a multimeter to the two wires going into the resistor and measure its resistance directly. But I thought I would mention that since it is in your text. When we talk about a resistor, though, in an electrical circuit, that is completely abstract. We're just talking about a piece of the circuit that has resistance. So it could be something like one of these physical resistors. It could be something like a light bulb. A light bulb has a resistance because of a very thin filament made out of a substance with a high resistivity, low conductivity. And so that light bulb we could write in the circuit as being resistor 1, and it has a resistance of 100 kilo ohms or whatever. So it doesn't matter when we're diagramming a circuit what the resistors are. If you're building a circuit to do something in particular, you need to know what the resistors are and what they're there for. But when we're analyzing the resistance of a circuit, all resistors are sort of created equal. We don't need to care much about what the resistance means for the rest of this chapter. So what I want to talk about now are just these rules, these mathematical rules for determining the resistance of a circuit that has multiple resistors in it. So for example, I gave the example when we were drawing diagrams of circuits a while ago. Suppose you've got a circuit with a battery, say a 9-volt battery, and a resistor that has a resistance of 3 ohms, and then a resistor of 2 ohms, and then a resistor with a resistance of 1 ohm. And I want to know, what is the current going to be flowing through that circuit? I know V, I know I. Ohm's law says V is equal to IR, so I should be able to use Ohm's law to find that electrical current, V equals IR. In order to do that, I need to know the resistance of the entire circuit. So I need to understand sort of what is the circuit that I've created here. Well, the circuit I've created here is just 3 resistors, 1, 2, 3, in series with one another from the positive to the negative terminal of the battery. If we think about the definition of resistance and the relationship between resistance and resistivity, the resistance is equal to the resistivity times the length of the resistor divided by the cross-sectional area. And we think of these resistors as just being pieces of wire, even if they're not, even if they're ceramic resistors. It's pretty easy, I think, to guess what the effect is of having multiple resistors one after another would be, which is that effectively is just increasing the length of the resistor. So if you have three resistors, R1, R2, and R3 in series with one another, the total resistance of those resistors in series is just equal to R1 plus R2 plus R3 plus dot 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 dot. So to find the resistance of resistors in series, in this case, it would just be 3 ohms plus 2 ohms plus 1 ohm equals 6 ohms. So these three resistors in series with one another, just connected one to the next, from the end of one to the beginning of the next, end of one to the beginning of the next, with no branching of the circuit going on. Every electron, if you want to think about it this way, every electron in this circuit has got to go through all three resistors before it makes it back to the other terminal of the battery. So the total resistance is just the sum of those resistances, and we can write for resistors in series, our total is equal to the sum of all the individual resistances. So if I wanted to know the current flowing through this circuit here, the current is just the voltage divided by the total resistance, which in this case is 9 volts divided by 6 ohms, which is equal to, what's that, 1 1/3, right? Yeah, 1 3, no, 1 1/2. Okay, 1.5, 1.5 what? Amps. Okay, a volt divided by an ohm is equal to an amp. So 1.5 amps of current would flow through this circuit. The situation is a little more complicated if the resistors are in parallel with one another. If the resistors are in parallel with one another, first let's draw a circuit. We'll just draw a circuit with two resistors. So we've got a battery. We've got, we'll draw it the easy to understand way. Well, let's draw it with 3. 1, 2, 3. Just label them R1, R2, R3. Let's say this voltage here is 1.5 volts. And let's say the resistances of these are, oh, I don't know, let's say 2 ohms. R2 is, let's make them all the same. 2 ohms. R3 is 2 ohms. Okay, so you've got 3 2-ohm resistors wired in parallel, meaning that the current splits and has 3 branches, 3 different checkout lines it can go through before coming back together and making its way around the circuit. And suppose I wanted to know what is the current through this part of the circuit due to that 1.5 volt potential difference and these 3 2-ohm resistors. Again, if we think about the relationship between resistance and resistivity, the resistance of an object is equal to the resistivity times the length divided by the cross-sectional area. Remember we said increasing the cross-sectional area available to the electrons is like opening another checkout line at the grocery store at Walmart. If you think about what you're doing when you've got 3 resistors wired in parallel, you're essentially increasing the surface area available for those electrons to pass through. And since the resistance is inversely proportional to the surface area, the expression for the relationship between the total resistance and the individual resistances is that it's equal to the sum of the reciprocals of the individual resistances of the resistors wired in parallel to one another. So the total resistance of this circuit is 1 over R1 plus 1 over R2 plus 1 over R3. Okay? So that's going to be equal to 1 over 2 ohms plus 1 over 2 ohms plus 1 over 2 ohms. 1/2 plus a half plus a half is 1.5, or 3 halves. I got to be careful with my units here. 3 over 2 ohms. 1 over that, which is 2/3 of an ohm, or 0.667 ohms. Okay? Oh, went off the bottom there. 0.667 ohms. In general, when resistors are in parallel, we write that the total resistance is equal to, or actually, the way we would usually write that is 1 over the total resistance is equal to the sum of 1 over the individual resistances, sum from 1 to n, however many resistances there are. Notice that the total resistance of these 3 2-ohm resistors in parallel with one another is less than the resistance of every individual resistor. That putting resistors in parallel with one another decreases the total resistance, whereas putting resistors in series with one another always increases the total resistance. When you put resistors in series, no matter what they are, the total resistance will always be greater than the greatest one. When you put resistors in parallel with one another, the resistance will always be less than the smallest one.